share. Okay, so now I think you can all see my screen. So let us start with this Gram-Schmidt algorithm. So before formally writing what I'm going to write for Gram-Schmidt orthogonalization procedure, I wanted to understand a couple of things that we have done, right? So first of all, for given vectors x and y, so in general in Rn, but I will draw a diagram for R2 only. It doesn't matter. You can sort of visualize this in Rn. I will tell you how to visualize this in Rn. But given vectors x and y in Rn, inner product of x transpose y is summation xi yi, I from 1 to n. That's how we defined this. And inner product of x transpose x is actually 2 norm of x square. That's how the norm function was actually defined. And we defined angle between the vectors x and y. So cos theta was actually equal to x transpose y divided by norm of x into norm of y. So in this, I may forget to write down this subscript 2, but you have to understand that if I don't write subscript 2 to the norm, then it really means that I'm talking of 2 norm of a vector. Okay, so these are the 3 entities that we had defined. And if you see the diagram, okay, so what is the diagram I'm drawing? So the diagram I'm drawing is that this is my vector x, this is my vector y. This is my vector x and y. Okay, so so with this vector x and y, we really want to understand how this inner product and angle between the vectors and everything really comes into the picture. Okay, so in order to do that, let us try to do this geometry. Okay, so suppose I complete this right angle triangle. Okay, I complete this right angle triangle. This angle between the two vectors is theta. This is a right angle triangle. Then, okay, so this can be done. Let me do it in another way. Okay, let me do it in another way, so that if I draw that diagram, then probably understanding is easier. Then we'll come to this particular case. So let me draw this diagram. Okay, so first I will draw two vectors. So this vector is x, this vector is y. Okay, this angle is theta, and I will put a perpendicular down here. Okay, then according to the rules of trigonometry, can you tell what is this length and what is this length? So this length is obviously length of the vector, which is norm of x, correct? So this length is norm of x. Then this length, do you all agree, is actually norm of x into cos theta, and this length is norm of x into sine theta. So that using the Pythagoras law, sum of squares of sides is equal to sum of squares of sides is actually equal to the square of the hypotenuse. So you have norm x square cos square theta plus norm x square sine square theta, which is equal to norm x square, which is nothing but the length of the hypotenuse. So do you understand what I did here? Just use simple thing. So this particular number, okay, so the length, this particular length is actually called as scalar projection of vector x on y. This is the scalar projection of vector x on y. That's the length we are talking of. And if I multiply this vector, this scalar, so if I multiply this scalar into cos theta into y, okay, so into y divided by norm of y. Okay, so the unit vector in the direction of y, then this is called as projection of x on y. Okay, and now if you see, you substitute this value of cos theta, then if you substitute the value of cos theta, you will realize that what is the formula for projection that you get. Okay, so this is something that I just wanted to tell you, that this is the geometric meaning. This is what geometry really tells us. So it is like you project it onto y at the foot of perpendicular. So that length norm x into cos theta, that length, the scalar value is actually the scalar projection. And you take the unit vector in that direction, multiply the unit vector to the scalar, then what you get is actually the vector, okay, the projection vector. Okay, so that's what you see as that's what you see this. Okay, so this is what we are really looking at. And then now you see the thing that I was trying to do previously, then it's not really a difficult thing, you can still do it. So this right angle triangle is easy to visualize, so I just gave this right angle triangle. So this is what this cos theta projection and all this business really is going to be. And now when we understand this, I am going to make use of these things. Okay, so I'm going to make use of these things. So so let us write these things down. Okay, so what is the objective given vectors x1 and x2. Okay, so I am given two vectors x1 and x2. So these vectors are given to me, x1 and x2. What do I want to do? I want to construct q1 and q2 such that what happens? Span of x1 is equal to span of q1. So I want this condition to be satisfied first. Second condition is that span of x1 x2 should be same as span of q1 q2. So I want these spans to be equal at the second stage also. So that means that and what is the third condition? The third condition is that q1 q2 is an orthonormal set. So I will, for the time being, for the sake of this diagram, I will just assume that this is linearly independent. Okay, it is not necessary. If this set is not linearly independent, what happens we will see when we analyze this algorithm. But for the time being, let us consider that this set is linearly independent. Okay, so what happens? So I will draw this diagram. So I will not so this circle actually, okay, so let me try to draw it again. So this circle, let us say, is a circle which is all the vectors of unit length. Okay, so this vector is x1, this vector is x2, and the circle is all norm 1 vectors. Okay, all norm 1 vectors. So the first vector is x1 vector. Okay, so geometrically let us see what is happening. So this is given. So what I want to do, I want to construct q1 and q2. Okay, so what is the first objective in q1? Q1 should be such that q1 and x1 the span is same. So clearly if q1 and x1 span is same, then what do you want? You want q1 in the same direction as x1, then it doesn't matter. Then the span of q1 is same as span of x1. So in principle, q1 vector is same as x1 vector. But what is the additional thing that we require? The additional thing that we require is that q1 is q1 q2 is an orthonormal set. So in an orthonormal set, what is the necessity? In orthonormal set, the necessity is that you should have all the vectors with norm 1. So in order to construct q1, what will we do? In order to construct q1, what we do is the following. So this is q1. So how do I construct q1? I look at this vector x1 and I find the unit vector. So what is the unit vector? Unit vector will go only up to this length, right? So this is my q1 and my x2 is still like this. So this is my x2 and this is my q1. Is the span of q1 same as span of x1? Obviously, the span of q1 is same as span of x1 because q1 is actually unit vector in the direction of x1. So that's not a problem. So this step is clear. Then what do I do? What I do really is now I look at projection of x2 on q1. I look at the projection of x2 on q1. So angle between them is theta. So the projection of x2 on q1 is actually q1 transpose a2, okay, into q1. So the projection is q1 transpose a2 into q1. So I project this x2 onto this x1 and this is what I get. And once I get it, what will I do? I will subtract that projection from here. So geometrically, what is the vector that I am getting? So the geometry is saying that the vector that I will get is this vector. So this is your q1. This is your x2. Correct. So this is x2, this is q1, and I construct a vector which is okay. So this angle between x2 and horizontal axis is really weird now for me. So let me see if I can draw this so that horizontal axis does not match with what I am trying to do. So this vector that I draw here is so this vector in this direction is basically minus q1 transpose x2 into q1. That's the vector that you have, and you add these two vectors x2 and this. So the parallelogram that will come into the picture and you will get this vector. So okay, maybe I should draw it a little better so that you understand what is happening. This is this vector, and the parallelogram, if you do, you will get this particular vector. Okay, so this vector is what you will really get. And the last step is actually take a unit vector in this direction. Okay, so take unit vector in this direction. So when you take unit vector in this direction, you will get orthogonal vectors. Okay, so this is your q1, and this vector that you see here was your vector x2 minus this q1 transpose x2 into q1, and you take unit vector in this direction and that becomes your q2, and there is a right angle between these two vectors. Okay, so that's what we have done. So now, okay, all the diagrams is in place. Let me try to explain. So if you have not understood so far what we have done, let us try to understand what we have done. Okay, so what I have done is that in this particular step, the first picture here, in the first picture, I have just drawn two vectors x1 and x2. In the second picture, what I do is I construct q1 from x1. That construction of q1 from x1 is straightforward. I think there is no difficulty in understanding that construction. The key is third figure. What is happening in third figure? What is happening in third figure is that I am taking projection of x2 on q1. What is projection of x2 on q1? The projection of x2 on q1. So q1 is basically norm 1 vector. So this is norm 1 already. So for us, this is q1. And what is the projection of x2 on q1? The projection of x2 on q1 is norm of x2 into cos theta. That's what you have. So norm of x2 cos theta into q1 is the projection of x2 on q1, right? So that's what I have here. So once I have that thing here, then what am I going to do? What am I going to do? I am going to replace cos theta by this particular formula where this is q1 and x2 is x, right? So you have this x2 transpose divided by norm of x2 into q1. So if I write this calculation here, projection of x2 on q1. So projection of x2 on q1 by formula is that 2 norm of x2 cos theta into q1. Okay, so this formula I am using this formula I can write down this projection here. So this is norm of x2 cos theta, I can norm of x2, and cos theta I can write down x2 transpose q1 divided by x2 into norm of q1 is 1 anyway into q1, correct? So that's what I have here. So this norm gets cancelled to this norm and I am left with x2 transpose q1 into q1. So do you understand how I get this particular vector here? X2 transpose q1 into q1. So x2 transpose q1 is same as q1 transpose x2. So I can write this as q1 transpose x2 into q1. So this is what I get. So this vector is actually the vector which is projection of x2 onto q1. So that is what this vector is. Okay. So what I am going to do is, so this vector is somewhere in this direction. So this vector I take negative of it, so that vector goes down here, right? So that vector goes down here. So that vector is basically this, right? And then I complete the parallelogram. So when I complete the parallelogram, addition of these vectors x2 and this vector is actually this diagonal entry, right? So diagonal is what we have. So that diagonal entry is basically this entry that I have written here. It is not norm 1, so make it norm 1. When I make it norm 1, it goes here. What is the advantage of doing this weird operation? The advantage of doing this weird operation is that now q2 is actually perpendicular to q1. In fact, this particular vector is perpendicular to q1. How can you check that? You can check that very easy. So the calculation algebra is very easy. I hope you understand geometry, what I did. So at this point, if you have any doubt in the geometry, please ask me. I will try to resolve that doubt.
In the third diagram,
Yeah.
I understood the projection that x2, the projection of x2 is again taken on q1 in order to extract q2, right?
Yeah.
So, for what was the purpose of this purple arrow in the third quadrant?
Third, that purple arrow. So basically the projection that you see here, is along this direction, in this direction. Okay. So we are taking negative of that vector. So that is this vector which is parallel to the green vector that you see here. So this green vector and these vectors which are parallel to each other, they have that minus q1 transpose x2 into q1 magnitude. So I will complete the parallelogram by addition of x2 with this vector minus q1 transpose x2 into q1. So I will complete this parallelogram the way I have completed it, and then you see this diagonal of the parallelogram is actually this vector which I have denoted here, and you take unit vector that will give you q2. That's what.
In this Q1 is the diagonal of the parallelogram. Q2 is the diagonal of the parallelogram.
q2, not q2 exactly, this vector x2 minus q1 transpose x2 into q1 is the diagonal of the parallelogram. You will take unit vector in that direction to get orthonormality condition satisfied. So this vector is alright perpendicular with q1. These two vectors are perpendicular to each other.
Sir,
So
to
this
get
you,
the
yes.
to find the unit vector, we have to get the to normalize that x2 minus q1 transfers x2 q1 value, sir.
Yeah.
Okay,
Yeah.
sir.
So divide by the norm of that vector. That's all.
Okay, sir.
Sir, sir, can you please
I
explain
didn't follow
the
the X. Go ahead.
Uh-huh.
Go ahead, sir.
What is it? Can you ask once
I
again?
did not follow why X2 minus why X2 minus how X2 minus came in this. I didn't follow that.
So what we are basically doing is, see, there is q1 and you want to find out an orthogonal vector to q1. Now in order to find out the orthogonal vector to q1, what do you have to do? So what you have to do is the following, right? So see, it is something like this. You have a vector which is x2 sitting somewhere here, and you have a vector q1 which is an orthonormal vector, right? So this is x2. So in here, what is happening in this diagram, two-dimensional diagram, you see what is happening. If q1 is fixed, then you know what is the orthogonal direction. What is the orthogonal direction? Orthogonal direction is this direction, the one that I just drew. So this direction is orthogonal direction to q1. So q2 has to be a vector in this direction. Do you all agree? That is what has to be done. Now, in
Yes,
order to
yes.
obtain the vector q2 on this line, what will you do? What will you do is that you will try to remove the part of component of q1 from x2. So you will want to remove x2 from q1 part from x2. So basically what is happening, if you see, x2 can be written as a linear combination of q1 and q2. Do you agree? So q2 is a unit vector in this direction that I have drawn. It is perpendicular. So q1 and q2 are orthogonal. So if they are orthogonal, then x2 can be written as a linear combination of q1 and q2. You agree with this? q1 and q2 will form actually a basis of R2. So that linear combination is a unique linear combination. That is also fine with you. And now
Yes,
because
yes.
q1 and q2 are orthogonal, what is it that we know? The thing that we know is that the linear combination is basically x2 q1 into q1 plus x2 q2 x2 q2 into q2. Is that right? Or if you want to write it in this q1 transpose x2 into q1 plus q1 sorry, q2 transpose x2 into q2. Correct? That's the linear combination that you have. Do
Yes,
you agree?
yes.
Yeah. So if you agree to all of this, then what is it that we are really doing? The thing that we are really doing is that, okay, so what is it that I know? In this equation, I know q1 because I already have q1. I know x2 because I already have x2. This x2 is already known to me. I do not know what is q2 transpose, or I basically I do not know what is q2, right? That's the thing that I do not know. Do you agree? So I have to calculate that q2. Basically, that's what I have to do. So what will I do? I will do x2 minus q1 transpose x2 into q1. That will give me q2 transpose x2 into q2. Do you all agree with this equation, the last equation that I have written?
Yes, now it is understood.
So
So
this thing is basically coming from the algebra. What is the geometric meaning of this? The geometric meaning of this is that you look at this particular entity. This particular entity is actually projection of x2 on q1. That is the geometric meaning of this. And what you are doing, you are trying to remove that projection of x2 on q1 from x2. So see, x2, because of orthonormality of q1, q2, can be sort of compartmentalized into different directions, x1, q1, q2, q3, q4, so on and so forth. Do you agree what I'm saying? So what I'm saying is that I am trying to remove the direction which I already know. So I know the direction of x2 in terms of q1. I am just removing that through the projection. So I just removed that. So whatever is remaining now is purely in the direction of x2. Do you agree? So this particular vector
yes.
is purely in the direction of x2. Now what do I want to do? I want to normalize this vector. So because you see this particular vector, this particular number setting here is basically nothing but a scalar. So okay, so this green highlighted thing that you see here is basically nothing but a scalar. So what I am doing by subtracting the component of x2 in the direction of q1, what I am really getting is something which is purely in terms of x2. That's all I am getting. So if I get that, then I can normalize it, and after normalization, I can say that, see, I have got a unit vector in this direction of q2. So that's what basically I did in this third diagram, in this third figure, geometrically. So maybe, yeah, whichever way you understand it easier, that's your choice. So I feel geometry is more intuitive, so I try to explain through geometry first. If geometry is not really something that you can digest, then this is the algebraic manipulation. That's what I have really done. Okay, so if this understanding is clear, then we can sort of generalize it to the further directions. Is that okay?
Yes, sir.
Thank you very much.
Excellent. Yeah. And now what you can check for yourself is that this is, so this vector, this green vector, so I will write this vector once again. So this vector you can check is perpendicular with q1 actually. So x2 minus q1 transpose x2 into q1 is orthogonal to q1. So what is orthogonality of two vectors? The dot product between the two is 0. So I will write down, so to check, so you check q1 transpose into x2 minus q1 transpose x2 into q1. Correct? That's the inner product that we have to look, and we have to show that this inner product is actually equal to 0. So you have the first term q1 transpose x2. Then you have the second term q1 transpose x2 into q1, correct? So now this term is actually the scalar like alpha, so it can come out because of the associativity of the inner product. So this is nothing but q1 transpose x2 minus q1 transpose x2 into q1 transpose q1, but q1 transpose q1 has to be equal to 1 because q1 q2 form orthonormal set. Because q1 q2 form orthonormal set, this guy is 1, so this guy actually is scalar 1. So what you are left with is q1 transpose x2 minus q1 transpose x2, which is equal to 0. So you actually show that q1 and x2 minus q1 transpose x2 q1, these two vectors are orthogonal to each other. So you have got an orthogonal direction all right now. So when you have got an orthogonal direction, you just normalize in that orthogonal direction. That's it. That's all you will do. So when you normalize, so what is normalization? Normalization is that you have x2 minus q1 transpose into x2 q1, you divide by 2 norm, x2 minus q1 transpose x2 into q1, you divide by 2 norm, and this will be your q2. Okay, so this is the normalization process. Is that okay? So I hope the algorithm is clear, what we are really trying to achieve. I hope this is clear to all of you. If there is any doubt still, I think we can get it sorted here, because this is the first algorithm, probably a non-trivial thing that you have seen in this course, probably the first non-trivial thing. So if you have still any doubt, you can get it clear.
Could you explain the last two equations once again, please? If
So the orthogonality argument, you mean?
yeah.
So you want to show that this vector, which I am highlighting by red. So this vector is orthogonal to this vector. So what is it to say that two vectors are orthogonal? You take dot product between the two vectors and show that the dot product is 0. So if the dot product is 0, then you will say that the vectors are orthogonal to each other. I think there is a lag, so you still cannot see the highlighted.
So this
Yeah, now you see the
minus
two red highlighted vectors. I am saying this vector and this vector. So I am taking dot product between these two vectors. So I am taking q1 transpose into this big vector x2 minus q1 transpose x2 into q1, correct? So now I will use the properties of inner product. So the properties of inner product says that if you have z transpose into bracket x minus y, it is same as z transpose x minus z transpose y. So that's what I have done here. So I'm just opening the bracket in this particular step. Now in this particular step, you see you have inner product. So you have q1 transpose, then you have q1 transpose x2 into q1 transpose. So q1 transpose x2 is like a real number because it's a inner product. So it's a real number. So this is something like y transpose beta into y. So y transpose beta into y is beta times y transpose y. So that's all I have done. So this beta has come out here. So this beta has come out and I have q1 transpose q1 here. But q1 is of norm 1 because it is coming from orthonormal set. q1 transpose q1 is 1. So you are left with q1 transpose x2 minus q1 transpose x2, which is actually equal to 0. Is that okay?
this x1 minus this big vector x1 minus q1.
No, there is no x1. There is x2 minus
x2 minus q1 transpose x2 into q1.
q1. Yeah.
It
Yeah.
represents
What happens to that?
so it represents the value of q2, right? That we are trying to find out.
It does not, it is not q2, it is an orthogonal vector to q1. It is not q2. Q2 is here. So q2 is basically that big vector divided by its norm, because the vector that you have obtained, the orthogonal vector, may not be of norm 1. It may not be of norm 1.
Okay, so this is just the orthogonal vector.
Orthogonal vector. Now in order to make it orthonormal collection, you have to have that other condition satisfied, that all the vectors in that collection should be of norm 1. So you do this particular thing, normalization, and by doing this normalization process, in other words dividing by its two norm, you get the vector q2. Is that all right?
Sir, I have one question, sir.
Yes.
Sir, if I ask geometrically, you have said that x2 minus q1 transpose x2 into q1 is projection. Sir, in this slide,
Yeah. Yeah.
No. The previous slide.
Here.
In this, yes, sir. So in this slide, this part is the projection of x2 on q1, right? x2 minus q1 transpose x2 into q1. This is projection of x2 on q1.
Projection of x2 on q1 is this part, the red highlighted part that I am showing here.
So, sir,
q1
now
transpose x2 into q1.
q1 transpose x2 into q1.
That is the projection of x2 on q1.
Okay. I thought that x2 minus no.
No,
Okay,
no,
sir.
no. So you are removing that projection. So what basically you are doing is you are removing. So this vector is in the direction of q1. No, you see this vector, the projection vector is a vector in the direction of q1. So it is somewhere in this direction, right? So according to this diagram, so this vector will be something like this, right?
Okay. Thank you, sir.
So that is the vector. You are taking negative of that. So negative of that goes here. then you are doing x2 minus this vector. So you are completing the parallelogram basically. And when you complete the parallelogram, then you get this vector which is in the direction of q2, right?
Q2. Now it is orthogonal. Okay, sir.
Correct, na? So
Yes, yes.
orthogonal, it is orthogonal from geometry also you can see, and from
Mm-hmm.
algebra also you can see. Okay.
Yes, sir.
So I
Thank you,
hope
sir.
this is clear. Yeah. Okay, fine. Excellent.
Sir,
Then, yes.
sir, in this example, we did first x1 and then x1, x2. If
Yeah.
we do like we start with x2, so the
Yeah.
results of q1 and q2 will be different, right?
Yeah. Results of Q1, Q2 will be different.
So if we have like n x's, so we'll have like various
No, so
q's,
you choose
q1
an order.
permutation.
See, you. So right now also in this algorithm also there can be a difference between Q1 and Q2, no?
Yeah, yes, sir.
So why did you choose Q1 to be this vector only in this particular slide? Why did you choose the vector Q1 to be this particular vector only? You could have chosen Q1 to be this vector also. The span of Q1 is still same as span of X1.
Yes, sir.
Correct, na? So here also there is no uniqueness guaranteed.
Okay, sir.
So do you see the point?
Yes, sir.
Yeah. So what do we mean by uniqueness? Almost up to the subspaces and so on and so forth. So I think when we go to matrices, we will be more clear on this. When I write this thing down in matrix notation, I think it will become more clear. Okay. So I think at least this much we should do. Let us write down the algorithm. Okay. So I will write down the algorithm for general case, and you see now it is not really difficult to understand what is really happening. Algorithm Gram-Schmidt orthogonalization. Okay. So what is given? Given are k vectors x1, x2 up to xk. K vectors are given in an n-dimensional space. And what are we doing? So I am assuming that let x1 up to xk okay, I will include this linear independence in the algorithm itself, so that algorithm becomes the most general possible thing. So for I is equal to 1 2 up to k, what are you supposed to do? The first step is orthogonalization. So you write down q I tilde to be equal to ai minus q1 transpose ai into q1 minus so on so forth qi minus 1 transpose ai into qi minus 1. Okay, that's what you do. Then you do the second thing, which is test for linear dependence. If qi tilde is equal to 0, then you break this loop, you quit this loop. If it is
So
not,
what is A? A is X here, right?
oh sorry, it is xi, I'm sorry, this is xi. You are right, I am looking at x1 x2 x1, absolutely. And normalization. So what is the normalization? I form qi to be equal to qi tilde divided by qi tilde h2. Okay. So these are the three steps I keep on doing until I is equal to 1 to k. So the step that we just looked at was the step when we were given only two vectors. So k was equal to 2 So in k equal to 2, this is what we had done. Okay, so I think this is the algorithm that you have to understand. And now you see the linear dependence, linear independence, that is also taken care of in this particular second step. So let us try to analyze this Gram-Schmidt orthonormalization. Okay, so let us try to understand it step by step. So I will write down few properties and then we will try to prove. Okay. Let this be linearly independent. So if that is true, then the first thing is qi tilde is not equal to 0. Okay, so for any I, qi tilde is not going to be equal to 0. q1 up to qi are orthonormal. The third step is xi is a linear combination of q1 up to qi, and the fourth property is qi is a linear combination x1 up to xi. So this is something that is really very useful. So these are the four properties, and these four properties can be very easily proved, from the algorithm that we have written. Okay, so these four properties actually help us. So these two properties here give us the guarantee that you are not arbitrarily constructing the orthonormal vectors q1, q2, qk. You are constructing this vectors q1, q2, qk in such a way that the spans are also same. So span of x1 is same as span of q1, span of x1 x2 is same as span of q1 q2, span of x1 x2 x3 is same as span of q1 q2 q3. These are the conditions that are satisfied. Those things are basically said in property 3 and 4. q1, q2, qr are orthonormal. That was our objective, to construct an orthonormal set from the independent set, and we are assuming that it is independent, so any qi tilde is not equal to 0. So if qi tilde equal to 0, so what is qi tilde? So in this particular case, this was qi tilde. So if any qi tilde was equal to 0, then this is what we would opt. Okay, so that's what we have here. So linear dependence if qi tilde equal to 0. Okay, so do you want to try right now? I'll give you 4-5 minutes. All the things that I have explained here in previous slides, all the things that I have explained here on this slide actually are enough to prove everything that I am asking you to do in these things. Okay, so the time is almost up. So why don't you sort of give it a try yourself to prove these things in couple of minutes that are left. Any property that you can take. So I think property 3 and property 4 is easy. Property 2 is also easy. I have already given a proof at the last line of this slide for the independent orthogonality. So why not do this? So the only thing that you have to remember is that this particular vector that I have written here is basically q2 tilde in the notation of the algorithm. This is q2 tilde, right? So if this is q2 tilde, then why don't you give it a try and prove these properties. First property, maybe you just skip. I will show you how to do the first property. But apart from first property, I think if you want to do the other properties, it's a good idea to do. Why don't you give it a try? If there is a difficulty, there is a problem, I can help you.
Sir, can you show the properties again?
Properties, okay, yeah. These are the these are the properties. So in the meantime, if there is any other doubt from the previous lectures or whatever we did today, if you want to ask, you can feel free to ask them now. Uh,
Sir, I have a doubt.
yes.
Sir, I understand that span is a linear combination of two vectors, but in a coordinate geometry space, how do we visualize it?
No, so what do you want to visualize?
Suppose there is a span of two vectors. So,
Span of two vectors is what you want to visualize. Okay, so if you
yeah,
want to visualize span of two vectors, span of two vectors is basically all possible linear combinations of these two vectors, right? So suppose
yeah,
x and y are two vectors you are talking of, and alpha and beta are the scalars, then alpha x plus beta y is basically what you are looking at, right? So
yeah,
alpha x plus beta y, if you see, then you take any value of alpha. So in particular, you take alpha to be any real number and take beta equal to 0. Then you will get all the vectors on the direction of x.
yes, sir.
Same thing will happen when you take alpha is equal to 0 and beta any real number, you will get all the vectors in the direction of y.
Yes, sir.
Now you take positive values for x and y. You take positive values for x and y. Sorry, alpha and beta. Any positive value for alpha and beta. Then what will happen? You will have a scaled version of alpha x and beta y in the direction of x and y.
Yes, sir.
Then you do a parallelogram. When you do the parallelogram law, the diagonal will be the sum of the two vectors.
Yes, sir.
So if x and y are vectors like this, then in this area between the positive directions of x and y, all the vectors are getting covered.
Okay, sir.
Same thing, if you negative multiply, then there are four parts, right, between the two lines x and
Yeah,
y, right? So each part will get completely covered by taking alpha positive, beta negative, alpha negative, beta negative, alpha negative, beta positive, and alpha beta positive. And when you get alpha equal to beta equal to 0, you will get 0 vector. So you'll get entire plane.
okay.
Sir, can you go to the previous slide?
Am I clear? Do you understand what I said?
Yes, sir.
Yeah, because for some reason my laptop just shut down, so I was not sure. Okay, so I'll just okay. So Lavina, do you want to ask something from the slides?
No, I just have a general question. Like, is there any book
Yeah.
you're referring so that can be in case I get
So
stuck while?
I already told there are two books I am referring to. One is Introduction to Applied Linear Algebra, Vectors, Matrices, and Least Squares by Stephen Boyd. This book I am told is available on Stephen Boyd's website itself for free download. And the second book I am following is the book by Gilbert Strang, Linear Algebra, Learning from Data. So these are the two books that I am following. So I think for next couple of
Chat?
weeks, huh?
Can you write the name on the chat?
I already shared. So if you see the first PDF document that was shared in this chat history, the books have been mentioned. There is a PDF file in which these books are given. If you want, I can write once again, but this is already given in the note. Somewhere it is already written. I will write again, no problem.
Thank you.
Sir, can I try to prove two properties?
That is fine. If you are able to prove, that is fine. That's okay.
Okay.
Any other doubt?
Hello, sir.
Yes.
Sir, hello.
Hello.
Yes, Satyajit, please speak.
Sir, I have got an older version of Gilbert Strang, Linear Algebra and its
That book
applications.
is
Will
no,
that be okay?
that book is not what we are studying. That book does not have anything that
Okay.
I will cover. Okay, so that book was written for a different audience long back. The book that I am mentioning just came out last year in 2019. Okay, so it
Okay.
is a
Okay.
very recent book. Yeah.
Okay.
Who else want to ask?
Hello.
Yes.
Hello. Sir.
So
Sir,
So
my
maybe
whiteout recording.
I'll just stop recording.